Good morning, students. In the previous video session we have discussed about the Hooke's law and its experimental verification. I believe that you all practiced the derivation, and today we are going to have a new topic, Poisson's ratio. Actually, what is this Poisson's ratio? From where this name Poisson's came? So before going through the topic, you have to know about one thing. You see, we all have the practice that taking a rubber band and stretching like this. We know that while you stretch this rubber band, when you apply the force on this rubber band stretch and its length increasing. So when the length increases, what happened to its diameter? So what happened to its diameter? Its diameter get decrease. So this is what happened in everyday life we are doing. When we get the rubber band, we just do it like this. So here on diagram is given. You know this thing, when we stretch the rubber band or wire, it will be like this. So its length will get increase and its diameter will get decrease. So the diameter decreasing part, we can use the word lateral strain. You can tell contraction. You can use the word elongation, contraction. Elongation, where the length increases, there we can say elongation, and where the diameter decreases, that part we can say contraction, or you can use it lateral strain or longitudinal strain. So this part and this part, both part diameter is getting decreasing, so you can use lateral strain, and both these and length is getting increasing, you can use the word longitudinal strain. Now so to quantify this or to calculate this, a French scientist Poisson's developed a ratio. That is what we are saying, Poisson's ratio. So to calculate this elongation and this contraction or lateral strain and the longitudinal strain, a French scientist whose name is S.D. Poisson. So he made a relation, he found out a ratio. That ratio is called Poisson's ratio, and this ratio is like this, mu. Poisson's ratio, you have to use the symbol mu. Mu is equal to lateral strain by longitudinal strain. Lateral strain by longitudinal strain. This is what we are saying, Poisson's ratio. So Poisson's ratio means, how we can define means, it is defined as the ratio between lateral strain to longitudinal strain. Or you can use, it is defined as the ratio between the relative expansion, relative contraction to the relative expansion. That is what mu is equal to lateral strain by longitudinal strain. And you can use the symbol for lateral strain, you can use d by d, and longitudinal strain L by L. This is what in symbol wise. What is this small d? What is this capital D? Capital D and capital L is, when you are taking an unstretched wire, the original length we are taken as capital L, and this capital D means its original diameter. So after you stretch the wire or the rubber band, its diameter is changing, so the diameter we are using small d, and for that length we are using small l. So you can write this Poisson's ratio, mu is equal to minus d by d. This L we are taking upside down, so L by small l. So this is called Poisson's ratio. Mu is equal to minus small d by d into capital L by small l. Here small d means the diameter before, diameter after stretching the wire, and the capital D means diameter before stretch the wire, and the capital L means the length before stretch the wire, and the small l means the length after stretch the wire. Now, what is this negative symbol? Here one negative symbol is there in this. The negative symbol shows, you know that when we stretch this rubber band, here a deformation happening. This deformation produces in one direction cause another direction. So the deformation in one direction produces the deformation in another direction. When you stretch this rubber band, two direction elongation and contraction producing. One direction this rubber band is getting elongate, and another direction the rubber band is getting contract. So this contraction and elongation which is causing in two direction, that is the reason why we are using minus symbol here. So this is what Poisson's ratio, and how you can define means it is defined as the relative expansion, the ratio between the relative expansion or relative contraction to the relative expansion. In formula wise, mu is equal to lateral strain by longitudinal strain, and you can use the symbol minus small d by d whole divided by small l by l, and mu is equal to minus d by d into l, capital L by l. Again remember that small d means after stretching the diameter changing, that d is what, small d, and capital D means the diameter of the original diameter of the wire. So capital L the original length, and small l after stretching length. Okay, now elastic energy. This is on derivation, on 3-mark derivation. You see, this elastic energy means, actually the same example you can take, you are stretching this rubber band, and here the length is increasing and the diameter decreasing. When we stretch this rubber band, you know this thing, every object, it has some internal force. It has some internal force. When we stretch this rubber band, we are doing some work against this internal force. So, whenever we are doing some work, what is happening? We are doing this work against the internal force. So, when we stretch this rubber band, we are doing some work done, and this work done we are doing against the internal force. And this work done is stored as elastic potential energy in the rubber band. When we stretch the rubber band, it possesses some elastic potential energy, and this elastic potential energy from where it get? We are doing some work done against the internal force. When we do some work against this internal force, that is what? That is equal to the elastic potential energy. So here we are going to find out the work done to stretch this whole length. For that we have choose a wire of length capital L and a cross sectional area A. So one wire we can take and stretch the length of wire. Its length is capital L and its cross sectional area, we can choose it as capital A. So when we stretch this wire, we are doing some work against the internal force, and this work done is equal to the elastic potential energy. Now we can find out the work done to stretch this wire. For that, we know that our general formula W is equal to F into D. So here we can choose dW is equal to F into dl. and here dl means for the small length, and we are using it for small length, that's what we are using dw. And we know that we need to find out the f value. So if you want to find out the f value, we have to choose the Young's modulus formula, which we have discussed in the previous video session. So dw is equal to f into dl. This you can take the equation number 1. And now we have to find out the f. To find out this f, we have to use the Young's modulus formula. Y is equal to f by a into L by L. So L by L. So this is what Young's modulus formula. This you have to take equation number 2. Before, from this Young's modulus formula, we have to find out f. So take f by a into L by L is equal to y. And now we have to find out this f. So keep this f this side and take this a and L another side. So f L is equal to y al. Now f equal to y al divided by capital L. This you can keep equation number 2. Now what we have to do means, we need to find out the Ogden W, and here we have found the f from this Young's modulus formula. Y is equal to f by capital A into L by capital L by small l, and from that we have found this f. So for that I have taken this f by A, L by L this side and y another side. Now f is equal to what? It is a and l taken upside, so y al. So f is equal to y al divided by capital. Now substitute equation 2 in equation 1. Substitute equation 2 in 1. So substitute this f value here in equation 1. So dw equal to, instead of f we have to write this value, y al divided by capital L into dl. So this is the work done for small work done. For the small length, how much work we did means OA small l divided by capital L. So this is for the small length. Now we have to find out the total length, total elongation. For that, what we have to do means, we have to integrate this equation. You have to take this equation 3, integrate equation 3, and we have to give the limit from 0 to the whole length L. So from the 0 to L length of this wire, we have to find out the work done. So integrate this equation 3, integrate equation 3. So what we will get? Integration dw equal to IA. Now L we have to choose a dummy variable for our easy integration. So instead of L you can use L dash. Why we are using this dummy variable means, we are giving the limit 0 to L. So without confusing, we can substitute the limit value, so that we have to use a dummy variable here. L instead of L we are using L dash divided by L into dl. Now I'll integrate dw, we will get w, and before integration take all the constant value. Y is constant, area of cross section is constant, and the capital L all we can take it outside. So y a divided by capital L 0 to L dash dl dash we have to give. So here from this step equation 3 L is there, dl is there. Without confusing, we have to integrate, so that we are changing this L to L dash using a dummy variable. And now integrate. LDL. LDL means it is in the form of x dx. We know x dx means what? X power n plus 1 divided by n plus 1. X dx integration is x power n plus 1 divided by n plus 1. So here L dash dot dl. So what will come integration? It will be the answer. L power L dash power 1 plus 1 divided by 1 plus 1. So L dash square by 2 we will get integration. We have to substitute W is equal to YA divided by L. After integration we will get L dash square by 2. Limit, upper limit, lower limit, upper limit L. Now next step what you have to do means we have to apply the limit. Instead of this L dash we have to apply the upper limit L and the lower limit 0. Now W equal to YA divided by L. First apply the upper limit. Instead of L dash we have to use L. So L square by 2 minus 0. So answer W equal to Y A by L, L square down 2L we will get 2L. Y A L square by 2L. Now we know that this is the work done we got. Now what we have to do means we know that F is equal to YAL divided by capital L. From this equation, Y is there, A is there, L is there, 2 is there. So take all these separately. So W equal to Y A. This L square is splitting into L square I am splitting L into L divided by capital L. Now YAL divided by capital L, you can choose, you can write what as F. So W is equal to, you have 2 also there, W equal to F L divided by 2. So we can write this equation W equal to 1 by 2 F L. Now this is a work done 1 by 2 FL. Now what we have to do means we have to find out the energy density. Energy density means we know that energy density means what? Energy per unit volume. Now here we have found the work done for the whole length. And from this we are finding the energy, because the work done is equal to the elastic potential energy. So that elastic potential energy we have to find out for each volume, each per volume how much energy is stored. So for that we have to use E equal to elastic, U is equal to elastic potential energy divided by volume. We know that this work done is equal to or same as the elastic potential energy. So U equal to 1 by 2 FL divided by A into capital L. Area into length is the volume. So V is equal to area into length A into L. From this equation you can write U is equal to 1 by 2 F divided by A, L divided by L. So you can write U is equal to 1 by 2 F by A means stress F by A means stress and L by L means strain. So this is the energy stored, elastic energy stored when we stretch a rubber band or this wire. So again you see we have to find out the work done. For that we are taking dW is equal to F dot dl, and we need to find out this F value. For that we are choosing the Young's modulus formula. We know that Y is equal to F by A dot L by L, and from this formula we are finding area, and what we will get? We are finding the force. So F is equal to, this A will go here, L will go here, this L will come down, so A small l divided by capital L. Now we are substituting this equation 2 in equation 1. So what we will get? dW is equal to YAL divided by capital L into dl. Now we have to find out the work done for the whole length, so that we are integrating. So integrating the equation 3, while integrate we have to choose the dummy variable for L. Just for L we are writing L dash. After integration we can apply the limit without confusion, so that we are using L dash. So YA L dash by capital L dot dl dash we are using. Now YA capital L is constant, so we have to take it outside. We have to integrate L dash dl. So integration x dx means we know that x square by 2. So here L dash dot dl dash, so L square by 2. So L square by 2 we are writing. Now applying the limit, upper limit minus lower limit. So apply limit is L, upper limit is L, and the lower limit is 0. While applying this we will get YA L square by 2L capital L, and we know that YA small l divided by capital L is F. For that substitution we are splitting this L square is L into L. So YAL divided by capital L we can write it as F capital F. So work done we will get W is equal to F small l divided by 2, and we have to find out the energy per unit volume, that is equal to the energy density, how much energy stored, elastic energy stored. So U is equal to elastic energy divided by volume. So this half FL divided by volume means area into length AL. From that just we are rearranging and writing 1 by 2 here, F by A, and small l by capital L. And what is this F by A? It is called stress, and L by L, small l by capital L is strain. So that we can write U is equal to 1 by 2 stress into strain. And you can use the textbook page number 58, Poisson's ratio. It is a very important 3-mark question. You have to just write the definition and this formula, Poisson's ratio, and the derivation, page number 59, elastic energy derivation. You have to practice this derivation. And the next is the application of elasticity. While taking the Young's modulus session, I told you we have to know the value of each metals, the Young's modulus value of each metals, because it is very important for the engineers. It is very important for the engineers to know how much each metals bend. That is what here the application of elasticity. You know this thing, while making a bridge, while construct a bridge by using the metal, while construct big buildings by using these metals and all, they have to know, they must know about the Young's modulus of each material, metals like this iron Young's modulus, steel Young's modulus. That's what I told yesterday in the page number 57. It is given the Young's modulus values for each material. Steel, how much aluminium, how much copper, how much iron and glass. Every material's Young's modulus values is given. By using these Young's modulus values, easily they can find out which material is suitable for constructing this bridge. How much this metal bend. This all the thing they can find out by using these Young's modulus values. So that's what to make big bridges and high machinery part and all, they are choosing the steel, because steel is higher Young's modulus values than any other metal, than the iron, than the copper, than the aluminium, than the glass, everything. That's what this steel is used to make the bridges and for the high machinery parts and all, they are making by using this steel. And this construction buildings and all, concrete, while doing the concrete and all, they choose this iron, because its iron value Young's modulus comparatively it is smaller than the steel. That's what the iron is used in the construction field for this concrete and all. So then this aluminium and all, vessels and all making. So because its bending is more, its Young's modulus values are less. So that is what it is very important this to know about the Young's modulus values for each and every material. So my dear students, you have to go through page number 58 of Poisson's ratio. It is an important 3-mark question. You can see the last line, SD Poisson proposed a ratio known as Poisson's ratio, which is defined as the ratio of relative contraction to relative expansion. And then you can continue the formula 7.10, then mu is equal to, you can write the formula. Then the derivation 59, elastic energy. Practice this derivation. See you all. Bye bye. Thank you all.